Please check your own answers on ionic bonding part 1. At the end, you may move on to the next section. So what is the fundamental difference between ionic and covalent compounds? The answer to that question is fairly straightforward. It's how electrons are arranged. Covalent, shared in a region between bonding atoms. For ionic, electrons are transferred from metal to nonmetal, and they actually exist on the electrons that are involved are actually existing on the anion, leaving a cation behind to attract. Given a chemical formula such as CaCl2, what are two ways that you can determine the bond type in this compound? Okay, well, one way would be that we have a metal and a nonmetal. The other way would be to find difference in electronegativity. And here it should be greater than 1.7, indicating that it is ionic. What is a formula unit and how does it differ from a molecule? Well, first of all, let's go with molecule. One way that it's different is that molecules have covalent bonding, and they represent an individual particle for a formula unit. Ionic bonding and it represents a simplest ratio. H2O represents a physical object. Every water molecule can exist technically independent of other water molecules, even if it doesn't happen very often. One water molecule should be able to exist independently. On the other hand, if we have something like NaCl, NaCl represents a 1-to-1 ratio between ions. This is not something that we would expect to find in nature, but it is the simplest ratio. So one's a ratio, one's a physical object. Ionic compounds tend to be made up of a metal with low first ionization energy and a nonmetal with a strongly negative electron affinity. How does this combination lead to ionic bonding? Probably the easiest way to say this is that the properties lead to electron transfer from metal to nonmetal. Very different attractions. First ionization energy, low attraction to electrons, strongly negative electron affinity, strong attraction. To electrons. Using Lewis dot diagrams demonstrate ionic bond formation with calcium and phosphorus. Okay, well, if we have calcium, 2 dots, phosphorus with 3 dots, we're going to transfer an electron, transfer another electron. That leads to a calcium plus 2 ion, but a phosphorus that doesn't have an octet, so we bring in another calcium, transfer an electron, that leads to a phosphorus with a negative 3 charge, but we have a calcium with an extra electron, so we bring in another phosphorus. We transfer one of the electrons, that gives us another calcium with a plus 2, and we're going to have to bring in another calcium to supply the extra electrons. 2 more electrons are needed. 1 more calcium can supply both of those electrons. So we end up with another calcium and another phosphorus with a ratio of 3 calcium to every 2 phosphorus. We're going to repeat this with aluminum and oxygen. Aluminum, group 13, has 3 dots. Oxygen, group 16, has 6 dots. Aluminum, the metal, transfers electrons. That gives a satisfied oxygen with a negative 2 charge. Aluminum still has an extra valence electron, so we bring in an oxygen. Transfer 1 more electron. That gives us an Al3+. Now we have an oxygen that needs another electron, so we bring in an aluminum, 3 electrons, transfer 1 to take care of the second oxygen. There's another oxygen 2-, but we've got an aluminum that has 2 electrons to give, so we bring in an oxygen that has a need for 2 electrons. So with that gives us another aluminum and another oxygen. So that gives us the formula of 2 aluminums for every 3 oxygens. Next, what happens to the energy of the atoms involved in ionic bonding? What happens to their stability? During bonding, no matter if it's ionic or covalent, energy decreases, stability increases, regardless of the bond type that's forming. We then want to list several properties of ionic compounds and their corresponding properties for covalent compounds. Ionic compounds have high melting points and boiling points. They're good conductors in liquid phase. These are ionic. They are good insulators in solid phase. They're brittle, solid, and crystalline. That's a few. We may have others that we could list there. Covalent, corresponding properties, lower melting points and boiling points, poor conductors in all states, so that actually makes them good insulators. In all states. They tend to be waxy when solid or liquid or gas at room temperature. So they're not going to be brittle, and instead of being solid and crystalline, they tend to be, if they're solid, they tend to be waxy, but they, and with lower melting points, and they also have a tendency to be liquids and gases depending on the substance. We can also add over here that these are electrolytes. It's all of them. Most of these are non-electrolytes. Acids are the major exception. And that completes the answers to your student practice questions.